In our previous lesson, we talked about binary trees in general. Now in this lesson, we are going to talk about binary search tree, a special kind of binary tree, which is an efficient structure to organize data for quick search as well as quick update. But before I start talking about binary search trees, I want you to think of a problem. What data structure will you use to store a modifiable collection? So let's say you have a collection, and it can be a collection of any data type. Records in the collection can be of any type. Now you want to store this collection in computer's memory in some structure, and then you want to be able to quickly search for a record in the collection, and you also want to be able to modify the collection. You want to be able to insert an element in the collection or remove an element from the collection. So what data structure will you use? Well, you can use an array or a linked list. These are two well-known data structures in which we can store a collection. Now, what will be the running time of these operations, search, insertion, or removal, if we will use an array or a linked list? Let's first talk about arrays, and for sake of simplicity, let's say we want to store integers. To store a modifiable list or collection of integers, we can create a large enough array, and we can store the records in some part of the array. We can keep the end of the list marked. In this array that I'm showing here, we have integers from 0 till 3, we have records from 0 till 3, and rest of the array is available space. Now to search some X in the collection, we will have to scan the array from index 0 till end, and in worst case we may have to look at all the elements in the list. If n is the number of elements in the list, time taken will be proportional to n, or in other words we can say the time complexity of this operation will be big O of n. Okay, now what will be the cost of insertion? Let's say we want to insert number 5 in this list. So if there is some available space, all these cells in yellow are available, we can add one more cell by incrementing this marker end, and we can fill in the integer to be added. The time taken for this operation will be constant. Running time will not depend upon number of elements in the collection. So we can say that time complexity will be big O of 1. Okay, now what about removal? Let's say we want to remove 1 from the collection. What we'll have to do is we'll have to shift all records to the right of 1 by 1 position to the left, and then we can decrement end. The cost of removal in worst case, once again, will be big O of n. In worst case, we will have to shift n minus 1 elements. Here the cost of insertion will be big O of 1 if the array will have some available space. So the array has to be large enough. If the array gets filled, what we can do is we can create a new larger array. Typically we create an array twice the size of the filled up array. So we can create a new larger array, and then we can copy the content of the filled up array into this new larger array. The copy operation will cost us big O of n. We have discussed this idea of dynamic array quite a bit in our previous lessons. So insertion will be big O of 1 if array is not filled up, and it will be big O of n if array is filled up. For now, let's just assume that the array will always be large enough. Let's now discuss the cost of these operations if we will use a linked list. If we would use a linked list, I have drawn a linked list of integers here. Data type can be anything. The cost of search operation, once again, will be big O of n, where n is number of records in the collection or number of nodes in the linked list. To search, in worst case, we will have to traverse the whole list. We will have to look at all the nodes. The cost of insertion in a linked list is big O of 1 at head, and it's big O of n at tail. We can choose to insert at head to keep the cost low. So running time of insertion, we can say, is big O of 1, or in other words we will take constant time. Removal once again will be big O of n. We will first have to traverse the linked list and search the record, and in worst case we may have to look at all the nodes. Okay, so this is the cost of operations if we are going to use array or linked list. Insertion definitely is fast, but how good is big O of n for an operation like search? What do you think? If we are searching for a record X, then in the worst case we will have to compare this record X with all the n records in the collection. Let's say our machine can perform 1,000,000 comparisons in 1 second. So we can say that machine can perform 10 to the power 6 comparisons in 1 second. So cost of one comparison will be 10 to the power minus 6 second. Machines in today's world deal with really large data. It's very much possible for real world data to have 100 million or billion records. A lot of countries in this world have population more than 100 million. Two countries have more than 1 billion people living in them. If we will have data about all the people living in a country, then it can easily be 100 million records. Okay, so if we are saying that the cost of one comparison is 10 to the power minus 6 second, if n will be 100 million, time taken will be 100 seconds. 100 seconds for a search is not reasonable, and search may be a frequently performed operation. Can we do something better? Can we do better than big O of n? Well, in an array, we can perform binary search if it's sorted. And the running time of binary search is big O of log n, which is the best running time to have. I have drawn this array of integers here. Records in the array are sorted. Here the data type is integer. For some other data type, for some complex data type, we should be able to sort the collection based on some property or some key of the records. We should be able to compare the keys of records, and the comparison logic will be different for different data types. For a collection of strings, for example, we may want to have the records sorted in dictionary or lexicographical order. So we will compare and see which string will come first in dictionary order. Now this is the requirement that we have for binary search. The data structure should be an array and the records must be sorted. Okay, so the cost of search operation can be minimized if we will use a sorted array, but in insertion or removal we will have to make sure that the array is sorted afterwards. In this array, if I want to insert number 5 at this stage, I can't simply put 5 at index 6. What I'll have to do is I'll first have to find the position at which I can insert 5 in the sorted list. We can find the position in order of log n time using binary search. We can perform a binary search to find the first integer greater than 5 in the list. So we can find the position quickly. In this case it's index 2, but then we will have to shift all the records starting this position, one position to the right. And now I can insert 5. So even though we can find the position at which a record should be inserted quickly in big O of log n, this shifting in worst case will cost us big O of n. So the running time overall for an insertion will be big O of n. And similarly, the cost of removal will also be big O of n. We will have to shift some records. Okay, so when we are using sorted array, cost of search operation is minimized. In binary search for n records, we will have at max log n to the base 2 comparisons. So if we can perform million comparisons in a second, then for n equal 2 to the power 31, which is greater than 2 billion, we are going to take only 31 microseconds. Log of 2 to the power 31 to base 2 will be 31. Okay, we are fine with search now. We will be good for any practical value of n. But what about insertion and removal? They are still big O of n. Can we do something better here? Well, if we will use this data structure called binary search tree, I'm writing it in short, BST for binary search tree, then the cost of all these three operations can be big O of log n. In average case, the cost of all the operations will be big O of n in worst case, but we can avoid the worst case by making sure that the tree is always balanced. We had talked about balanced binary tree in our previous lesson. Binary search tree is only a special kind of binary tree. To make sure that the cost of these operations is always big O of log n, we should keep the binary search tree balanced. We'll talk about this in detail later. Let's first see what a binary search tree is and how cost of these operations is minimized when we use a binary search tree. Binary search tree is a binary tree in which for each node, value of all the nodes in left subtree is lesser and value of all the nodes in right subtree is greater. I have drawn binary tree as a recursive structure here. As we know, in a binary tree, each node can have at most 2 children. We can call one of the children left child. If we will look at the tree as a recursive structure, left child will be the root of left subtree, and similarly right child will be the root of right subtree. Now for a binary tree to be called binary search tree, value of all the nodes in left subtree must be lesser, or we can say lesser or equal to handle duplicates, and the value of all the nodes in right subtree must be greater, and this must be true for all the nodes. So in this recursive structure here, both left and right subtrees must also be binary search trees. I'll draw a binary search tree of integers. Now I have drawn a binary search tree of integers here. Let's see whether this property that for each node value of all the nodes in left subtree must be lesser or equal and value of all the nodes in right subtree must be greater is true or not. Let's first look at the root node. Nodes in the left subtree have values 10, 8 and 12. So they are all lesser than 15. And in right subtree we have 17, 20 and 25. They are all greater than 15. So we are good for the root node. Now let's look at this node with value 10. In left we have 8, which is lesser. In right we have 12, which is greater. So we are good. We are good for this node too, having value 20. And we don't need to bother about leaf nodes because they do not have children. So this is a binary search tree. Now what if I change this value 12 to 16? Now is this still a binary search tree? Well, for node with value 10 we are good. The node with value 16 is in its right, so not a problem. But for the root node, we have a node in left subtree with higher value now. So this tree is not a binary search tree. I'll revert back and make the value 12 again. Now as we were saying, we can search, insert or delete in a binary search tree in big O of log n time in average case. How is it really possible? Let's first talk about search. If these integers that I have here in the tree were in a sorted array, we could have performed binary search. And what do we do in binary search? Let's say we want to search number 10 in this array. What we do in binary search is we first define the complete list as our search space. The number can exist only within the search space. I'll mark search space using these 2 pointers, start and end. Now we compare the number to be searched or the element to be searched with mid element of the search space or the median. And if the record being searched, if the element being searched is lesser, we go searching in the left half, else we go searching in the right half. In case of equality, we have found the element. In this case, 10 is lesser than 15, so we will go searching towards left. Our search space is reduced now to half. Once again, we will compare to the mid element, and bingo, this time we have got a match. In binary search, we start with n elements in search space, and then if mid element is not the element that we are looking for, we reduce the search space to n by 2, and we go on reducing the search space to half till we either find the record that we are looking for or we get to only one element in search space and be done. In this whole reduction, if we will go from n to n by 2 to n by 4 to n by 8 and so on, we will have log n to the base 2 steps. If we are taking k steps, then n upon 2 to the power k will be equal to 1, which will imply 2 to the power k will be equal to n and k will be equal to log n to the base 2. So this is why running time of binary search is big O of log n. Now if we'll use this binary search tree to store the integers, search operation will be very similar. Let's say we want to search for number 12. What we'll do is we'll start at root and then we will compare the value to be searched, the integer to be searched with value of root. If it's equal, we are done with the search. If it's lesser, we know that we need to go to the left subtree, because in a binary search tree, all the elements in left subtree are lesser and all the elements in right subtree are greater. Now we'll go and look at the left child of node with value 15. We know that number 12 that we are looking for can exist in this subtree only, and anything apart from this subtree is discarded. So we have reduced the search space to only these three nodes having value 10, 8 and 12. Now once again we'll compare 12 with 10. We are not equal. 12 is greater. So we know that we need to go looking in right subtree of this node with value 10. So now our search space is reduced to just one node. Once again we will compare the value here at this node and we have a match. So searching an element in binary search tree is basically this traversal in which at each step we will go either towards left or right, and hence at each step we will discard one of the subtrees. If the tree is balanced, we call a tree balanced if for all nodes the difference between the heights of left and right subtrees is not greater than 1. So if the tree is balanced, we will start with a search space of n nodes, and when we will discard one of the subtrees, we will discard n by 2 nodes. So our search space will be reduced to n by 2. And then in next step we will reduce the search space to n by 4. We will go on reducing like this till we find the element, or till our search space is reduced to only one node when we will be done. So the search here is also a binary search, and that's why the name binary search tree. This tree that I'm showing here is balanced. In fact, this is a perfect binary tree, but with same records we can have an unbalanced tree like this. This tree has got the same integer values as we had in the previous structure, and this is also a binary search tree, but this is unbalanced. This is as good as a linked list. In this tree there is no right subtree for any of the nodes. Search space will be reduced by only 1 at each step. From n nodes in search space we will go to n-1 nodes, and then to n-2 nodes, all the way till 1 will be n steps. In binary search tree, in average case, cost of search, insertion or deletion is big O of log n, and in worst case, this is the worst case arrangement that I'm showing you, running time will be big O of n. We always try to avoid the worst case by trying to keep the binary search tree balanced. With same records in the tree, there can be multiple possible arrangements. For these integers in this tree, another arrangement is this. For all the nodes we have nothing to discard in left subtree in a search. This is another arrangement. This is still balanced because for all the nodes the difference between the heights of left and right subtrees is not greater than 1. But this is the best arrangement when we have a perfect binary tree. At each step we will have exactly n by 2 nodes to discard. Okay, now to insert some record in binary search tree, we will first have to find the position at which we can insert, and we can find the position in big O of log n time. Let's say we want to insert 19 in this tree. What we will do is we will start at the root. If the value to be inserted is lesser or equal, if there is no child, insert as left child or go left. If the value is greater and there is no right child, insert as right child or go right. In this case 19 is greater, so we will go right. Now we are at 20. 19 is lesser and left subtree is not empty. We have a left child, so we will go left. Now we are at 17. 19 is greater than 17, so it should go in right of 17. There is no right child of 17, so we will create a node with value 19 and link it to this node with value 17 as right child. Because we are using pointers or references here, just like linked list, no shifting is needed. Like an array, creating a link will take constant time. So overall insertion will also cost us like search. To delete also, we will first have to search the node. Search once again will be big O of log n, and deleting the node will only mean adjusting some links. So removal also is going to be like search, big O of log n in average case. Binary search tree gets unbalanced during insertion and deletion. So often during insertion and deletion we restore the balancing. There are ways to do it, and we will talk about all of this in detail in later lessons. In next lesson we will discuss implementation of binary search tree in detail. This is it for this lesson. Thanks for watching.